In this video, we're going to discuss recursive programming in Prolog. So recall that when we pose a query to the Prolog system, it's satisfied by following the resolution algorithm, which says, take each one of the subgoals of our query and match it to something in our knowledge base. Now, if it matches the head of a rule, what happens is the goal expands to include the body of that rule. So, if we want to empower repetition in our language, we just need to add recursive clauses into the body of our rules such that when they expand into our goal, then our goal now needs to once again unify with that same rule. Now, recursion in Prolog works like recursion in a lot of other languages. We have two parts. We have a base case and a recursive case. In Prolog, these are typically represented as two separate clauses, a disjunction of two separate terms, where one represents the base case and another represents a recursive case or a recursive rule. So consider, for example, summing a range of values between two integers. So we'll say the sum range function, or sum range rule, from a, b, and result. So it takes in three pieces of information. Takes in might be a bit of a misnomer. We'll say this is true if the sum of all the integers in the range from a to b, we'll say inclusive, is equal to result. Okay, so this is a description of what this thing needs to be. Now, this needs to be recursive because we're going to solve it one piece at a time, because a and b might be any different values, so we can't just explicitly code the summation. So we need to have some repetition in here, so we're going to need to have a base case and a recursive case. So the base case, in this case, is that a and b have reached the same value. So for some range, like we saw it in scheme, a is the smaller of the two values. We'll assume that a is smaller and b is larger. Then a is just going to be growing each time through this recursive function, recursive clause. And when it gets to this base case, then a equals b. So we'll say sum range with a, b, and result. And this will be a rule that's true if a is equal to b. Notice I use double equals here. We don't want to unify them. We want to say if they already have the same value, that's great, then this is the rule to be using. And then in that case, we will say result and a should unify. Now, this will only work if the result variable is an unbound variable. And we'll see how all this sticks together once we see how the recursive case works as well. But the basic idea is once we reach this case, we're going to take the result and store a value in it. And now, our recursive case. So in our recursive case, it's going to be a rule again. So we have sum range, a, b, and result. Now notice these two things have the same head. So we have sum range AB result and sum range AB result, which means they collectively together define this predicate sum range as we've seen it here. So we need both a base case and a recursive case, two separate rules that together collectively define one predicate. Now, for the recursive case, what we're going to do is add one value from this range into not so much a running total. We're going to do it with a recursive pattern as well. So we're going to defer the sum of one value into the result of adding up the rest. So we'll say the sum from 1 to 10 is 1 plus the sum of 2 to 10. And the sum from 2 to 10 is 2 plus the sum from 3 to 10. Okay, so to do that, we're going to have to get a few things. We're going to have to increment our starting value, so something like a1 is a plus 1. This might seem odd, but we'll discuss that again in just a second. Then we're going to have a recursive call, so sum range with that new value. So we've incremented a little bit. And same value for b. b won't change in all of these. And result. So result. Now we don't want this to be the same result as this one up here, right? This is going to be the final result of this call. So this is the result of everything from, let's say, 2 to 10, right? If we're passing in 1 to 10, a1 now has the value 2. So it's a plus 1. So this is the sum from 2 to 10. So this should be a different result, a temporary result. So this will be, we'll call it result 1. Okay, so it's our temporary result. And now what we need to do is take that temporary result and add the current value of a to get the total result, right? Again, if we said the sum from 1 to 10 is 1 plus the sum from 2 to 10. This is the sum from 2 to 10, so now I have to add that 1 plus part and put it into this variable. So we'll say result is a plus result 1. Okay, so this is the sum from 2 to 10. We'll add 1 onto that. Now we have the sum from 1 to 10. Now, how does this all work together? So this works a lot similarly to our recursive programming in schemes. So we have a recursive case here. We have some deferred work. We have to do the addition after we do our recursive call. So starting from, let's say, 1 and 10 again, we say, well, A1 is 2, and we say get the sum from 2 to 10. And that comes back to the top and says, okay, from 2 to 10, A1 is 3, get the sum from 3 to 10. Get the sum from 4 to 10, 5 to 10, 6 to 10, 7 to 10, all the way up. Eventually we get the sum from 10 to 10. That reaches our base case, so A equals B, 10 and 10, that's great. And then we'll say result, this variable here that we haven't yet come up with a value for, right? Each time we're passing in 2, 10, empty variable, 3, 10, empty variable. It's a different empty variable each time, but it's an empty variable. So when we get to here, we have 10, 10, and an empty variable, and we say put the value 10 into that empty variable. So that comes back to here and says, when I asked what's the sum from 10 to 10, it comes back with 10. Great. So now we'll say, well, the sum from 9 to 10 is 9 plus 10. And we'll store that in result, so that gets returned back through here. So then that comes back to where it was called from, where here we said sum the values from 8 to 10. And that was 9 plus 10, which is 19. So result 1 is 19, and we say, well, add 8 onto that 19 to get 27. On and on and on, all the way back down, and eventually we'll have all the answers, eventually we'll have all the answers back to our query. So let's try this out. Sure, let's just query this then. So sum range from 1 to 10. So notice when I'm querying this, I'm providing values for the information that I know. I want to have 1 and 10. That's the range of inputs. And then this last one here is left as a variable, a lot like when we were doing queries before when we weren't doing any repetition or anything. We left an empty variable, for example, for our coffee manager thing, we said manager X. And that would return, that's true if X is Bob. And this is the same sort of idea, except there's going to be more steps going on. So there's going to create a linkage of all of these results, where result equals A plus result 1, and result 1 equals A plus a different instance of result 1. And it goes all the way down until eventually this unifies with this, and it actually gets its value at that base case. Right, so we pass in actual values 1 and 10 for A and B, and an empty variable for R asking for an output variable. So you can think of that a little bit like a fishing hook. We're dropping in this empty variable, it's going to go through all this work. Eventually it's going to have a value put onto that hook, and then when it comes back out through the recursion, we'll have that value out in our query space. Helps if we consult our knowledge base, so recursion, and then try again. There we go. So the sum range 1 to 10 is 55. We could also ask a similar question, is the sum range from 1 to 10 equal to 55? And that comes up true. We could do that for other values as well. So sum range from 1 to 100 should be 5,050, something like that. Or we can put in a variable and see what it is. So we can kind of do these reversible a little bit. We have some arithmetic in there. So for example, we can't pass in an unbound variable for A. Similarly here, we can't pass in an unbound variable for B because it's asking, does B have the same value as A? But for R, we can either include a variable or not include a variable, and it will either return true or true with a value. Okay. So a few other things about this code. As I mentioned before, this A1 is A plus 1 might seem a bit odd. Normally we do something like this where we just say call the function sum range with A plus 1, B, and some sort of result variable. This is our output. Prolog doesn't let you do that. Prolog says you have to do all these steps individually, so we can't nest these in here. So we have to say figure out what A plus 1 is and then pass that value into the next instance of our function. Okay, and one other thing to point out here, this base case, while effective, is not necessarily the most abbreviated. In fact, seeing base cases like this is a little less common in Prolog. You're more likely going to see something more like this. If you say sum range A, which seems really strange, right? With this first one, you can say, okay, we're taking in two values A and B and an empty variable result, and then if A is the same as B, then result gets the value of A. It looks a little bit more like an imperative program, but Prolog is not an imperative programming language, as we've seen. So what this actually says is this will unify with any situation where the first two values are the same, and the third one's an unbound variable, which now has that value, right? So think if I asked sum range from 1 to 1 with r. Well, what is the sum of all the integers between 1 and 1? Well, it should be 1. So this will unify with this fact because 1 and 1. So we have essentially a situation where our start and end values are the same. We just use the same variable in both those spots. And now because that variable, in this case, is bound with the value 1, what happens when we use that variable as our result space here is that r will unify with a, and these a's unify with 1, so r unifies with 1. So it's a bit of an odd way of saying it. It's saying the exact same thing as this, just in a much more compacted notation. So it says if these two things are the same, then take that value and put it here as well. Okay. So that's the idea behind recursion in Prolog. So we have a base case and recursive case as before. The recursive case needs to, is dependent on a function call, we'll call it, to that same rule. So this sum range is dependent on a different sum range. And as always with recursion, it's very important that something in that recursive case shrinks the problem so that we eventually reach the base case. Otherwise, we end up in situations like we saw with the in the last lecture for the symmetric and transitive properties, where we had that infinite recursion because our problems weren't getting any smaller. Okay. Let's do another example. Let's do the Fibonacci sequence. So hang on, I never actually tested this new version of recursion, just to demonstrate that it actually works. There's the same thing. Okay. Now, I wanted to show the Fibonacci sequence, so let's do that next. So fib of 0 is 0, fib of 1 is 1, and otherwise the fib of n is equal to the fib of n minus 1 plus the fib of n minus 2. We've seen this example a number of times. It's most useful, at least in computer science as I've seen it, as an example for demonstrating branching recursion. So let's see what happens if we want to code this example in Prolog. So we have to deal with our base cases and our recursive cases. Now, as it turns out, we have a pretty simple definition of a recursive program here. So our base cases, in this case, we have fib of 0. So fib of 0 is 0. And we have fib of 1, which is 1. So the way to read these is this is our input. The first value is our input, and the second value here is our output. So if we're given a 0, we'll return a 0. If we're given a 1, we'll return a 1. So when calling this, if you want to know what the nth Fibonacci number is, let's say if we want to know what fib 0 is, we'd say fib 1 x, and that says that's true if x equals 1. That's how we know that the value of the first Fibonacci number equals 1. Now for our recursive cases, it's a little bit more involved, but it's no different than what we've seen before. So for the recursive case, we need to calculate n minus 1 and n minus 2, evaluate Fibonacci on those n minus 1 and n minus 2s, and then add everything together to get fib of n. So we get a rule for this. So we'll say fib of n is r. So again, the way to read this is the nth Fibonacci number is the value r. So if somebody's requesting this, they'd say fib of 10 is x. Okay. So x unifies with r. So in the end, whatever answer we put into this variable r in our rule will go out into the query as x. But then whatever value the user puts into n is the value we need to work with to create our answer. That's not going to work because I haven't reconsulted this yet, so let's just delete this for now. And let's create our rule. So first things first, we need n minus 1 and n minus 2. As we saw in the previous example, we can't just do that in line nested inside the Fibonacci call. We have to do that first. So we'll say n1 is n minus 1. Now notice you can't say n1 equals. We've seen this before. If you want the arithmetic to actually take place, to actually be evaluated, you have to say is. So is says evaluate this expression and then unify it with this unbound variable. Okay. We have n2 is and then n minus 2. In fact, we can do those on one line there just to keep our code a little bit compact. The next thing is we want to calculate the fib of n1 and the fib of n2. So we can say fib of n1 is r1 and fib of n2 is r2. So we call Fibonacci on this n minus 1 value and on this n minus 2 value, and we'll get back values r1 and r2 that represent the n minus 1 and the n minus 2 Fibonacci number. Okay. Now, all we need to do is take those two results and combine them together into our final result. So our final result needs to be put into this variable in the end, because the user, as I said before, is going to type something like fib 10 of x. X is going to get unified with r, so whatever value we put into r is going to get put into x. So we would say r is r1 plus r2. These two things should have numbers based on the previous lines, so we call fib of n1 to get the values for r1 and r2. So we'll just add those two values together to get the fib of n. Okay, so that's this one here, and that goes back to the user, and we're done. Save and reconsult. Okay, so you can say fib of 1 is 1, right? So for example, we can just run this where we pass in both our inputs and our outputs and to sort of verify information that we think we know. So if we run fib of 1, 1, we just get true in that case. It verifies our intuition. Alternatively, we could ask what is the value of these things. So we could say fib of, let's say, 7 is x. Now 7 goes into n, x unifies with r, and it walks through this whole recursion. So n1 becomes 6, n2 becomes 5, 7 minus 2, and it queries fib of 5 and fib of 7. Now, not walking through the entire tree, but those will come back with values for fib of 5 and fib of 4. Let's say, 6 and 5. I can do math. So fib of 6, fib of 5, and we'll have values for those, and we'll just add them together to get the value for fib of 7. There we go, 13. Right. That's basically it there. Now, there's a few things to notice about recursion in Prolog, though. First off is that order is very important. So, for example, what would happen if we rearranged the order of our base cases and our recursive cases? So I save this and reconsult recursion. So just pause for a second and think what would happen. What would happen if I queried, for example, fib 5r? Well, let's run it and see. Oof. The whole thing crashes. Stack limit exceeded, and you can see the error was many calls to fib with some weird numbers. All right. The issue here, we said fib of 5, which then asks, create 4 and 3 as n1 and n2, and then call fib of 4. It comes back up, and that's going to match with the head of our rule. So 4 makes it 3, call fib 3. And then 3 makes this 2, so call fib 2. And then this is 2, so that makes this 1, so call fib 1. Now notice when we call fib 1, we start at the top still, and we match that with our rule. So that makes this 0, and we call fib 0. And even then, we match with our rule. So we get fib -1, and we call fib -1. And again and again and again. The issue is we're always hitting this recursive case first. We're not asking, is it one of the base cases? If so, stop. And if not, then do the recursive case. We're saying, just do this recursive case every time. It never actually finds these base cases. So the stack fills up with all these recursive cases, and our code fails. So order is important. Generally speaking, the base cases need to be put first, and this is true in Scheme as well. If you have, for example, a cond statement, you'd have your base cases first, and then in the else would be the actual recursion. You're not going to just recurse and then check, oh, should I have stopped earlier? All right. One other thing to note here is if I run this same thing, so let's save, abort, reconsult, and let's ask fib5r again since it's here. I get r equals 5, which is true because it's 1, 1, 2, 3, and then 5. That's the fifth Fibonacci number. What happens if I backtrack here? We get a very similar looking error. The reason here is pretty similar as before. So the success here, fib5r returns 5, is true because eventually when we're calling these Fibonacci, these smaller Fibonaccis, we're eventually going to hit these base cases. Now at some point, we hit these base cases and it's going to return back up the call stack with all these unifications, where r is the sum of the two previous r's, and then we get our value that r equals 5. But if we put in a semicolon, we're saying, well, backtrack that, try something else. So what that's going to do is going to take one of the situations where it hit this base case and say, well, what else could we have done with that? So if it unified fib11 as one of the base cases, that's going to backtrack and say, well, I could also satisfy that by using this rule. So if fib11 then has 0, and 0 also calls fib11 calls fib of 0 and fib of -1. Fib of -1, as we've seen in the previous example, will then not match our base cases and go right to the rule. -1 gives us -2, -3, -2 gives -3 and -4, again and again for infinity, where we have then a full call stack. So the way to fix this specific problem is to just be a bit more specific in our recursive case. So our base cases are true for these two very specific values, 0 and 1. So our recursive case should only ever apply to the other values. Right now they also apply to 0 and 1. So what we should say is only use this recursive case if n is strictly greater than 1. Okay? If it's a negative number, just ignore it. There's no such thing as a negative Fibonacci number. If it's 0 or 1, only use the base case. Never backtrack and land on this recursive case. Okay, save, reconsult. Try it again. There's our success. And if we try to backtrack now, it lands on this recursive case, sees that n is not greater than 1, because n was bound to one of these base cases originally. That backtracked into here, where n was, let's say, 1 or 0 possibly. And neither of those are going to pass this test, so it then says false. There's no other values for fib5. All right. So I think that covers our recursive introduction video. In the next video, we'll take a look at recursion and iteration in Prolog.